Hi everyone, let's go ahead and get started with fine-tuning DistilBERT, MobileBERT and TinyBERT for fake news detection. So we are going to first discuss text classification architecture. So it is a kind of the text classification like we have seen previously. The only difference is here that we are going to use DistilBERT, MobileBERT and TinyBERT model. Along with that, we are going to use a different data set. And obviously thereafter we will be doing the benchmarking of all of these three models with the BERT base model. We have already gone through the research papers and we have seen that how fast MobileBERT is, how fast TinyBERT is, and how fast DistilBERT is. Then we will compare these with what research paper claims, whether those things are true or not. We will verify that by doing benchmarking by ourselves on fake news detection dataset. So this dataset is available at the Kaggle. The link of the dataset is given here. You can just copy this link from here. Let me just see if I can copy this from here. Okay, I just can't copy this from there directly. So I'm just gonna open that here. So here is a fake news. Okay, so this is available here. It says that if it is 1, that is the unreliable. If it is 0, that means it is reliable. And it is available at the Kaggle here. Okay, perfect. So as we have been discussing previously in the transformer architecture, a bare transformer available till the hidden state. Thereafter we need to add the classification head, and then the cross entropy loss function will be used to update these weights through the back propagation so that final prediction can be made there. Let's go ahead and see the coding part. So these are the necessary libraries which you need to install. Since we will be dealing here with the Excel dataset, so you need to also install here the Excel library as well if you do not have that one. Thereafter we are also going to import warning, and then we are going to filter out some warning messages. Generally, if you are in production, you don't do the warning filtering. But here we are doing just to keep our output clean. But if you are working in industry and you are writing your code in production, probably I would advise not to do this. Okay, let's go ahead and just run this. Thereafter, we are going to read this data. So what data we see here on fake news Kaggle, the same data I have taken from here, and then I have put that data into all CSV ML data files download in my repository so that you can access it easily. This dataset is available in Excel format, and that data is here, fake news.xlsx. So this data you can directly read in pandas data frame. So I'm reading it from my GitHub repository, and then I'm just gonna run this. Now you should be able to see this data. Okay, so this data is like around 50 it's 50 megabytes. So this might take a while to download this whole data and then print it out here. Okay, so it has downloaded this. There are around 21,000 rows there. I'm just gonna clear that so that I can save some space. This is the df, and thereafter I run here df.head. You can do. So I'm just gonna do here df.isNull.sum so that I can check here that how many null values are there. So seems like I have a lot of null values, so I'm just gonna drop those null rows so that I can have here a clean data set. So I write here df is equal to df.drop na. I'm just gonna disable my auto completion, otherwise it will just keep popping up there. Thereafter I write here df.isNull.sum. Thereafter you will see here there is no null value. You can also check the shape of the data frame just to verify that the current state. So it says that currently we are having around 18,000 rows. Earlier we had many more rows, but now it is coming around 18,281 rows. So this data set we will be using for our fake news detection. Let's go ahead and see how many fake news are there and how many true news are there. So you can check that with the df.label.value counts. It says that there is 10,361. 0 means, let me just verify it again. it says that 0 means reliable news, that means that is the true news, and here this one is the fake news. So 1 is fake news. There is around 8,000 fake news, and around 10,000 there is a real news. Okay, perfect. So this is all about in this lesson. In the next lesson, I'll do the data analysis, and thereafter we will start doing the data building and model building process. All right, I'll see you then. All right, let's go ahead and get started with the data set analysis page. So we will be doing here Seaborn and Matplotlib. So let's go ahead and do that. So I'm just going to do here import matplotlib.pyplot as plt. And thereafter, you know that we have our data into a data set df. In this, we are going to first of all get the label count, and that label is here 1 and 0. Okay, perfect. So I'm just gonna get that one. I say here that label underscore counts is equal to df label dot value counts, and in that I say here ascending is true. That means now it will be into ascending order. That's the label count. Thereafter I simply do here the plt. In fact, I'll do here label count dot plot dot bar plot, horizontal bar plot, and thereafter I write here the plt dot title, and in that I say here frequency of classes, and thereafter I say here plt dot so. That's all. So I see here there are around 8,000 fake news and around 10,000 actual or real news. Okay, so we have our data df. In this there are two text columns which we can use for the prediction. One is the title, another one is the text data. And our BERT model have a maximum input context size is 512 token. So we need to identify that how many tokens are there in title and text data on average. And we can say that around 1.5 tokens per word as per standard. So here I'm just going to write that 1.5 tokens per word on average. This is standard. So you have a word that might get broken into multiple tokens like we have seen previously. So just to accommodate that one, I'm just going to take word count, and thereafter I'm going to multiply it with 1.5 so that I can say that okay, this could be approx number of tokens. So here I write df title dot apply, and then I'm just going to write here the lambda function, and then I write here the length x dot split, and thereafter I just multiply this overall length by 1.5, something like this. And if I take here the mean of this one, so around 18 to 20 tokens per title or per rows on average there is. Okay, I'm just gonna remove this one, and then I'm just gonna store it into a title underscore tokens. This is the new column. And similarly, I'm just going to copy this whole thing from there, and then I'm just going to replace this title with the text. That means for the another column, and there you have it. So we have got here the data frame again that have two additional column, title token and text token. So this is on, you can say that approx number of tokens in this text column and approx number of token in the title column. Let's go ahead and plot this. So we can plot it using Matplotlib. So I write here figure, and then axis is equal to plt dot subplots, and then 1, 2, and then I write here fig size is equal to 15,5. Okay, so what I see here that 1, 2, that means I'm going to use here 1 row and 2 column. The figure size is going to be in That's going to be a width, and here it's going to be height. That's the 15 point or 15 inches in generally. So it's going to be quite high resolution or large image. Let's go ahead and plot the title token. So I just simply write here AX0 on first axis, or you can just, if you plot, then I'll just show you the reference. So this one becomes AX0 or axis 0, you can say that, and this one becomes axis 2, that is the AX1. And this whole thing is known as the canvas. So I'm just gonna, run here AX0, that's the first axis, and then histogram plot, and then I write here df title underscore tokens. It's like that, and then I just run this. Okay, so here I see here, but now I'm just gonna put here more number of bins. So I've been here total number of 50 bins, just to make it like a better plot. And then the color I'm just gonna make here like let's say sky blue is the color for me. I'm just going to choose this one. Okay, so I have got here sky blue color. This is the token distribution for the title. And then similarly, I can write here AX0 dot set title. And in this, I write here title tokens. This whole thing I copy from there and then paste it here, and then I write here the text token, and then here the text tokens. Thereafter I write here orange, then I just run this plt.show. Perfect. So what we get here, in fact not this one, okay, this is a little wrong, this need to be AX1. Alright, so here is the title token. In this I see distribution for the title, and here distribution for the text token, and generally seems like the number of tokens are quite large for the text data. It is going beyond 512. So it would be really very difficult for the model to learn from the text token, because mostly we will be cropping, or you can say that we will be truncating the most of the tokens from the text data itself. So it's not right to use the text token for the prediction. So it would be better to use the title token only. So we will be using title token for the prediction later on. So this title token, or you can say the title column, only be used for the tokenization and prediction. By keeping that in mind, let's go ahead and start building our data loader and train test split in the next lesson. Alright, I'll see you then. Alright, let's go ahead and get started with the data loader and the train test split. Our original dataset is stored in the data frame df, and we have decided to go through the title and then label. So label 1 represents the fake news, 0 represents their real news. So we are going to first load train test split, and then we will be splitting our dataset. Okay, so I write here from sklearn dot model selection import train test split. So here I decide that to put around 70% data for training, and then 20% data I decide for the, you can say that how much, the test data, and then the 10% I decide for validation. Okay, so this is a split which I decide to do. So I'm just going to do here first of all the train and test. In that I do here the train test split, and in that I pass here the data frame, and then I say here, okay, test size is 0.3. That's the 30% test size. So in this 30% is going to come, but I have decided the 20%. Later on I'll divide it again so that this can be divided into test and validation at the later stage. Okay, thereafter I say here stratify, so that the data can be divided properly into equal number of, or in equal proportion for fake news and real news in the test and train set. Then I say here the df and label. Okay, so from here I got the train set 70%, but test set is still having 30%. But I said that I'll be taking only 20% as test set. So I have to do here once again test and validation. So this is going to be again here the train test split. And in this train test split, I'm just going to put here the test, and then test size is equal to 1 divided by 3, and then stratify equal to test and then label. So in this, what happened here, since this test set we already know that it is 30%, so I say here 1 by 3, so it is going to put here 1 by 3 of the 30%. That's mean the 10% will be used into the validation and the 20% will be used into the test set. Okay, so that you can verify with the train.save and then test.save and then validation.save. And then obviously you can also verify with the df.save. So it's like that. So df.save have here 18,281. On average, you can say that around 12,000 would be the 70% of this one, and around 3,600 would be, that's the test set. So that would be around the 20%, and here would be, this one would be around the 10% of the original data set. Okay, so we have done with the train test split. Now currently our data frame here, what we see here, that this is into a pandas data frame format, and this pandas data frame is not accepted for the training. So we have to make it into a proper Hugging Face dataset and dataset dictionary so that Hugging Face model can accept these dataset for the training. So I write here from datasets import dataset and then dataset dict. So these two things I import here, and then I write here the dataset is equal to dataset dict, and in this dictionary I'm just going to put the 3 splits. So the first split I write here the train, and then I write here dataset dot from pandas, and in this I put here the train pandas data frame, and then I say here the preserve index is equal to the false, otherwise the index will be also stored into this train set. Thereafter I say here the test set. So the same thing I can just copy and paste it here from this whole thing. What I have there in the test set, only thing will be here the test. And thereafter I have here this validation set, and in the validation set I can put everything, but here this will be validation. Okay, so I have got now the data set. You can just print this data set, and then you will be seeing that this is a proper Hugging Face data set format. In this we have the title, author, text, label, so many other things. But in reality, when we are going to train our model, everything will be discarded, only label will be used and only the title will be used. Later on when we do the tokenization, then we will use the title for the tokenization, and then this will convert this text data into token IDs, or you can say that in a kind of the embeddings, which will be known as the input IDs, and that input IDs and label will be used for the training. Anyway, so these things we will be looking into the next section. Alright, I'll see you then. Alright, let's go ahead and get started with the data tokenization part. We already have our data into a dataset variable. It has a train, test and validation split. We are going to do the tokenization of this text data. Thereafter we will be having here input ID and labels and attention mask. Let's go ahead and import the auto tokenizer from the transformer. So from transformers import auto tokenizer. So this auto tokenizer comes from the auto classes. These classes are really excellent classes which provides you a facility where you can just define a model name. It will automatically fetch the respective tokenizer. Okay, so I say here the text is equal to machine learning is awesome I say here thanks KGP Talkie. So this text data I'm going to use as a sample text data for tokenization. As we know that we are going to do the benchmarking for DistilBERT, MobileBERT and the TinyBERT. So we will be doing this tokenization for the multiple models, and we will be here comparing the model architectures as well. So I define here first model checkpoint, that is the model CKPT is equal to DistilBERT base uncased. So this is DistilBERT model, and then I say here DistilBERT tokenizer, that is going to be the DistilBERT tokenizer. I say again here the auto tokenizer dot from pre-trained and then model CKPT. Let's go ahead and print this DistilBERT tokenizer. So this is the DistilBERT tokenizer. We will do the analysis later on. Let's go ahead and do the DistilBERT tokens. So here I get the tokens is equal to DistilBERT tokenizer, and then in this I say that DistilBERT tokenizer, and then I say here the tokenize, and in this I pass the data, that is the text, this one. Okay, so the same thing, I'm just going to copy this thing from here and then paste it here and here. The first I did for the DistilBERT, thereafter I'm going to do for the MobileBERT. So for MobileBERT, I say here Google, and then I say here MobileBERT base. I think base is not there, so you can just say that this is the model name. Actually, if you search this model name, you might ask that how do you know that these names. You can just simply search these model name here on Hugging Face, so it says that MobileBERT uncased model, or you can just simply type here MobileBERT, you will get here MobileBERT uncased model. So I'm just gonna copy this from there, and then I'm just gonna paste it here. It is exactly the same thing, and then here I say MobileBERT tokenizer is equal to the auto tokenizer from pre-trained model CKPT, which is this one, and then here I again say as MobileBERT token, and here I say MobileBERT tokenizer. The same thing is there. Okay, let's go ahead and get the TinyBERT from here. So I write here the TinyBERT. There are so many models for the TinyBERT. I'm just gonna select this one. So this one is English language model, which have 312 dimensions, 4 layer of the encoders there. So I'm just gonna select this one from here, and then I'm just gonna paste it here. So that is the TinyBERT general 4 encoder layer, 312 dimensions for the embeddings, or you can say that for the context vector. That's the model CKPT, and here I say TinyBERT tokenizer, auto tokenizer from pre-trained model CKPT, and here I say TinyBERT tokens, and then here I say TinyBERT tokenizer dot tokenize text. Okay, so in this what is happening, it is going to download DistilBERT base uncased tokenizer, then it's going to download MobileBERT uncased tokenizer, and then the TinyBERT tokenizer. So all the tokenizer is downloaded. Let's go ahead and compare these models. So I'm just gonna print here DistilBERT tokenizer, and then I'm gonna print MobileBERT tokenizer, and then TinyBERT tokenizer. Okay, now I'm going to compare all these together. If you remember, while we were going through the research paper of DistilBERT, MobileBERT and the TinyBERT, we discussed about some padding and some separator, masking, etc. And we also discussed about the vocabulary size. So it's total 30,522 vocabulary size for all of these models there. One thing you notice here that the model max length is defined here 512, but in these are not defined, but by default, yes, these have more model max length 512. Since it is not defined in Hugging Face, that is why it is representing here a max value, but it is not true there. It's 512 max model length. Each fast says that there is a fast tokenizer, and the padding side says that it's right padding, and so many other stuffs are there. Then there are special tokens. So all of these special tokens available in DistilBERT, MobileBERT and the TinyBERT I mean in all of these models. So the moreover with this you can know that overall architecture, internal architecture might be a little bit different, but working principle is almost same for DistilBERT, MobileBERT and the TinyBERT, because their vocabulary size, everything is same. Only thing is difference there, like their embedding size are different, some internal architectures are different. So if internal architectures are different, then obviously the total number of parameters would be also different there. That would be also different there. Okay, let's go ahead and do the tokenization for our whole data set. So the whole data set is stored in the data set. So we are going to use here a map function to do the tokenization. So I write here diff tokenize, and in this I'm just gonna call here the batch. So whatever the data will be passed in this batch, that will be tokenized. So I say here the temp is equal to DistilBERT tokenizer. So by default I'm going to use the DistilBERT tokenizer. There later on at a later stage I'll be doing other kind of the tokenizer benchmarking or model benchmarking in fact. So currently let's go ahead with the DistilBERT tokenizer. There I write here batch title, and then I write here the padding is true, and then I write here the truncation is true, and thereafter I write here return is temp, and then I print it here. Then I say here tokenize, and in this I pass some text data just to verify that if tokenization is happening properly. It says that something is wrong in this, seems like. Okay, yeah. So this text I cannot pass here directly, but in fact I need to pass the data set here. So I pass here the train data set, and in that I pass, let's say, the first two rows, and that's how you see you have input IDs. Thereafter you have attention mask. That's all. Input type IDs are not available. While going through the research paper of the DistilBERT, we knew that there, I mean, we had gone through there the sentence type IDs, or you can say the token type IDs. There was the additional key in the BERT model that got removed here. So it has only two keys, input IDs and attention mask. But if you see the MobileBERT tokenizer, then in that you will be having that token type IDs, because this token type IDs are not removed in MobileBERT and TinyBERT. It is only removed in the DistilBERT. So if that input type IDs are not available in DistilBERT, that means next sentence prediction cannot be done in DistilBERT as well. Okay, let's go ahead and apply the map function here. So I write here encoded dataset is equal to dataset dot map, and in this I pass here tokenized method, and I say here batch size is none and batched is equal to the true. So this means what it's going to do, if batch size is none, that's mean whole data will be used as a single batch, and then the tokenization will be done on the whole data in one go. Whatever the maximum number of the token is available in this whole data set, that will be taken as the max length for these input IDs, and thereafter whatever other token, whatever other rows which have a lesser number of the tokens, that will be filled with the 0. That is the padding token. Okay, and you also see there 102 and 101. So these are the special token. 102 says that this is a separator. 101 says that this is a CLS. So these are the special tokens, and this you can verify with this one. And if you check the second one, you will be seeing here that it starts from 101 and the last one is 102, because the second token here, second row data, have a maximum length there. So overall token is produced for that max length, whatever is there, and thereafter for rest of other rows it will be rightly padded with the 0 token. Alright, so this is all about in this lesson. Thanks a lot for watching this. In next lesson we will start model building. Alright, I'll see you then. Alright, let's go ahead and get started with the model building, and thereafter we will move to the model fine-tuning process. So before we get started with the model building, we have to make sure that we have our label to IDs and ID to label variable. So first of all, I'm going to create here label to ID. Why this label to ID is needed? Because when we go in production, there we have to tell that in Word that whether it is fake news or real news, and we also need these to pass this in the model as well, so that the model can do a proper prediction. So through the data at the Kaggle, we already know that here in the Kaggle, 1 is corresponding to unreliable and 0 is corresponding to the reliable. That means in this, if it is a fake, or you can say that if it is real, then it's a 0, and if it is fake news, then it is 1. And similarly, you can say that ID to label is equal to like this. So there 0 is corresponding to real, and whereas 1 is corresponding to fake. Okay, so this is just inverted dictionary there, label to ID, so that if label is given, you can directly get the ID, and if ID is given, you can directly get the label. Why we are doing that? If you remember in the data frame DF, so these labels are presented as ID only. Okay, so that is why we need these, just to avoid any confusion. So label to ID and ID to label is there. Let's go ahead and import here auto model from the auto classes. So I'm just going to do that. So from transformers import auto model, and then I'm also going to import torch as well, so that I can use some torch functions as well. Thereafter, by default, I'm going to define model CKPT here. So this model CKPT, I'm going to decide here DistilBERT base uncased. So I write here DistilBERT base uncased. Okay, thereafter I write here the model is equal to auto model dot from pre-trained, and thereafter model CKPT, and then I'm just gonna run this. Okay, so the model is loaded here. Once model is loaded, then I'm just gonna do here model dot config, and thereafter ID to label. So in this it says that 0 is label 0 and 1 is label 1. That doesn't seems right. So in this way, what you have to do here, you have to pass that configuration as well. So you have to first build that configuration as well. So if you remember our previous lesson where we did BERT fine tuning for sentiment classification, I'm just going to open that, and then I'll be showing you that how I did there, so that we can just directly copy that particular code from there, and then we can paste it here. Okay, just scroll it a little bit more down and down. Okay, here it is. So we have to identify first of all the device, although that device is needed for the sequence classification part, and thereafter I'm just gonna copy this whole thing from here. Okay, in fact, let's go ahead and copy this whole thing from here and then paste that whole thing from there to here. Okay, instead of using the auto model, we can directly use the auto model for sequence classification. We have here label to ID and ID to label. So these things I'm just gonna paste it here. Okay, so the number of labels are 2 here. It automatically becomes here, and if GPU is available, then this device will be having here a GPU, and config is equal to the auto config dot from pre-trained. Model checkpoint is here. So I'm just gonna paste that model checkpoint here, and then I'm just gonna remove this. So now what you see here, model checkpoint is DistilBERT base uncased, and then the config is equal to the auto config dot from pre-trained model CKPT label to ID and ID to label. So this thing is passed from there. Now if I just run this, and if I run this, now you see the 0 is real, 1 is fake. You can just simply here print model.config. So in this you will be seeing this whole model configuration. So whole model configuration says that attention dropout is 0.1% and internal dimension, or you can say that the context vector dimension is 768. Here ID to label is there and here is label to ID, and rest of other things like max position for embedding is 512. So it says that it can accept only maximum 512 tokens as an input. Total number of heads are here 12, number of layers are 6. So all these things you can see it here. Okay, but if you change this model CKPT from this point to, let me just copy the other thing from here, this MobileBERT, just so that you can have better understanding. If I make this one and I put a comment on this one, and if I just run this, so what you will see here, just let me show you. Okay, so this is first of all going to download MobileBERT uncased weight. Once it is downloaded, then I would be able to show you this model architecture. Okay, now if you run this and then if you open it, so in this label to ID, ID to label is same there. Hidden size is 512, embedding size is 128 only. Earlier, if you remember, it was 768. Now it becomes 128 only. And input token size is still 512. That is fine. Number of attention heads are reduced here to 4. And number of feed forward networks, this is the additional step here in the MobileBERT. And overall number of hidden layers you see here 24. Earlier in the DistilBERT it was 6 there. So some of these things you can see in architectural changes in the MobileBERT and the DistilBERT, and similarly you can identify for the TinyBERT as well. Okay, so for now I'm just going through with the BERT model here, DistilBERT model. In fact, I'm just gonna run this and then I'm just gonna print this model.config once again. If you want to go ahead with the DistilBERT as well, let's say in case if you are interested to know more about the DistilBERT architecture internally, you can also put that here, and then you can just run this one and then you can run this one. So in this, now you see the embedding size has changed to 312. This is what we discussed, and this is also here written. Other than that, the number of hidden layer is 4. That's the total number of encoder layer. It says that it is 4. Number of attention head here is 12. If you remember in MobileBERT, it was 4 only. And max position is 512, which is perfectly fine. It's the same as it is. Intermediate size is here increased. I think it's a 1200. But for other models, it was not there that much. I don't think that it was there. And moreover, other architecture seems like almost same. So there are some architectural difference, like the number of encoder layers, the hidden size, all these things are different for all of these models. That is why their number of parameters changes, because in TinyBERT it has around 15 million parameter and MobileBERT have around 25 million parameter, DistilBERT have around 67 million parameter, and BERT base have around 110 million parameter. So the internal architectures are different. That is why these parameter difference you can observe there. So I'm just gonna use this DistilBERT base uncased as a default model. Okay, so this is all about in this lesson. Thanks a lot for watching this. So in the next lesson, we will start with the model fine-tuning process. All right, I'll see you then. All right, let's go ahead and get started with the model fine-tuning process. So as we already know that once your data is given, you need to tokenize your data. Thereafter, embedding will be generated, and then there are encoder stacks depending on what type of model you are using. That means encoder stacks will be there. Thereafter, a final context vector will be produced there, and then there will be a classification head, and then finally the prediction will be done there. So this is the overall process, and we already have built our model here using auto model for sequence classification. So we don't need to worry about anything. Now what we need to do here, we have to build our training arguments, and then we can start doing the trainer. Other than that, we have to also put one attention here that we are going to use evaluator method. In previous lesson, in fact, let me just open the previous lesson notebook just for the reference, so it would be easy for you to understand there. So in a previous lesson, we had used here evaluator library to create here compute metric, and we had also used here sklearn library to build our compute metrics. We can use any of these method. Now this time we will be using this method to make our evaluation metric, so that you can get the overall understanding that how these evaluation methods are used there. Okay, so first of all we have to define here batch size from transformers import training arguments, and then you have to define here batch size. So I'm gonna do here 32 as a batch size, and then you need to tell training dir. So I say that training dir as train dir, that will be used as training dir. Then I say here training arguments, that's I say here training args is equal to training arguments. Okay, so as a reference, what you can do here, as we did in our previous lesson, as a reference I'm just gonna explain you that we used output dir, overwrite output dir, number of training epochs, learning rate, per device train batch size, weight, decay, and so many other stuff. So those things I'm going to use here as well. So we will start with output dir, or I can just copy this whole thing from previous lesson, and then I can put that whole thing from there to here, because most of the things are just copy from there to here. So training dir is train dir, overwrite output dir, number of train epoch, learning rate, everything is, it's like it don't depend on the type of the data set you are using. So this is kind of a task agnostic process. So I have just used this as a training argument as it is without changing anything. Once you have that, thereafter I'm also going to copy our compute metric as well. So this thing I'm just going to copy from previous video, and then I'm just going to put that here. Okay, so that is I'm putting here above this training argument, and I just run this. It also says that if you do not have evaluate, you need to install evaluate library. So I have ran this one, and thereafter I need to run this one. Now our training argument is ready. You can copy and paste it here, and you can run. So whatever the parameters we have used, these will be used. Other than that, other parameter will be used as a default parameter. So there are so many parameters here. Obviously we cannot define all these parameters, or we can define, but we don't want to change unnecessarily all the parameters. So it has some default set of the parameters, so it is going to use all those default set of the parameters here. So these are those parameters, those will be used as a default parameter. Thereafter, building this training argument, we need to build our trainer, so that we can do from transformers import trainer. Thereafter I write here trainer is equal to trainer, and then I write model is equal to model. We have already selected DistilBERT model, and thereafter compute metrics, I'm gonna select here compute metrics evaluate, this one, and it's going to give us the accuracy. Okay, so that's the compute metrics evaluate, and thereafter I'm going to use here the train dataset. So in the train dataset we have encoded dataset, train split, and thereafter we have evaluation dataset. So in that we again have encoded dataset as validation split. Thereafter we need to use here the tokenizer. So we are going to use here DistilBERT tokenizer. So these are things we are going to use here. I'm just gonna run this. Now our trainer is ready here. I can just copy and paste it here. So you don't see much in a trainer because it is an object there. So it shows that where this object is stored, but that we don't mind. Okay, so I'm just gonna run here trainer.train. So it is going to train the model for DistilBERT. Okay, so the training process has started. It's going to take some time to finish this training. So I'm just going to wait for some time, and thereafter we will do the model evaluation. All right, I'll see you in next lesson. Yeah, hi everyone. So model training has happened here, but seems like accuracy is not printed, but do not worry about that. Later on we will change this metric and then we will print the accuracy. For now it's okay because it took some time. So for retraining it will again take time. Just to make sure that we use correct evaluation metric, I'm just going to copy the sklearn method which we used in our previous lesson. So I'm just gonna get that one, but that we don't need to use immediately. So the later on we will be using when we will be doing this benchmarking. So for that purpose I'm just gonna copy and paste it here for the next lesson. For now we can go ahead with the model evaluation step where we have to print the classification report. So that part we can do without any issue. Okay, so first of all I have to do here the PREDS output is equal to trainer dot predict. So we have trained our data on train split and validation is done on validation split. Now we need to do evaluation on test split. For that I call encoded dataset test split, and now if you run this you will see that it will take some time, like some 10 to 20 seconds to complete this whole prediction. Thereafter you can print this PREDS output. You will see here that it is having here output in the form of logit because it is binary classification. So each row here have two classes, and these two classes are actually logits there. If you apply the softmax function thereafter, you will get the probability. Otherwise you can just take the maximum of these, you will get the index, and based on the index you can get the fake or real news classes. Okay, PREDS output dot metrics, I just run this. Now in this what I get here, I get the test loss where I have 0.2, that doesn't matter much, but here you see the test accuracy. So that's how we can see accuracy by using this compute metric evaluate method itself. And it is saying that it is almost 96%, which seems like quite good. Maybe trainer dot metrics, do we have anything like that? Seems like okay, it seems like we don't have. Otherwise I thought that if we have, so we can print that, but doesn't seems like we have a matrix anyway in a trainer. So that's what the test accuracy. You can get that using PREDS output dot metrics. Let's go ahead and get the predicted label. So that I'm going to store into ypred is equal to np dot argmax. Like I told you that in logits you can take the argument of maximum value. The argument means index of maximum value, and based on that you can say that whether it is fake news or real news. So I pass here PREDS output dot predictions, and that I'm gonna get row wise row. So I say here axis equal to 1, and y true is true label, and the true label is stored here in encoded dataset test split, and I'm gonna take all rows for this label column. Okay, so we have got ypred and ytrue. Now from sklearn you can import classification report, and then finally you can print the classification report. In classification report, the first value is y true value and the next one is y predicted value. So I pass here y true value and then y pred value, and thereafter you can also pass here the target names. So the target name I pass the list of label to ID. So list of label to ID is label target names there, and then I'm just gonna print this. So it says that accuracy for real news is around 96%, and the fake news, I mean to say that their precision, recall and accuracy is somewhere around 96% only. So the overall accuracy comes here 96%, which is impressive. Based on just a title, getting 96% of accuracy is really impressive. It's very good accuracy, you can see overall. Okay, so that's how you can evaluate the matrix. Like I told you at the beginning of this lesson, that in the next lesson we will be using compute metrics using sklearn, and thereafter we will be doing the benchmarking of MobileBERT, DistilBERT and TinyBERT models, and then we will be seeing that overall how much time it takes for the training. Okay, I'll see you then. Hi everyone, let's go ahead and do the benchmarking. So for the benchmarking, as I told you in the previous lesson, we are going to get the compute metric using sklearn. So it's the same as we have seen in the previous lesson. I had copied this code directly from the previous lesson where we fine-tuned BERT model. So in this you will see here we have label is equal to the pred.label_id. So in this prediction it is a dictionary. In that dictionary it has label IDs, and we also get the predicted values here using the maximum argument. So for the logits we take the index of the maximum value and then we say that okay, these are the predicted value. Thereafter for the labels and the predicted value, these are computed. These are used to compute the F1 score, and these are also used to compute the accuracy score. That's all is there in compute metric. You can just run this. Earlier we had used here, earlier we had used the compute metric evaluate method using the evaluate library, but seems like that did not print the accuracy while getting trained. It only printed the learning rate and the loss, overall loss, but we also want accuracy and F1 score and other custom parameter. If you want, you can build those in this method. So now I'll be using this one. So now for the benchmarking, as we have seen earlier that we have used here 3 methods, and those 3 methods are here. So I'm just gonna copy all these methods from there, and then I'm going to make here a dictionary. Thereafter I'll be running overall training in a for loop. So I write here model underscore dict is equal to a dictionary, and in this dictionary I'll be using this DistilBERT. So I'm just gonna copy this whole thing from there, and then I say it's like this. This is DistilBERT, and thereafter I need here MobileBERT, and for MobileBERT I'm just gonna copy this whole thing from here, and then I'm gonna take this, that is the TinyBERT, and then I just paste it here. This is for TinyBERT. Now we want to do this based on BERT model, so I'm just gonna use here BERT base model. So we are going to do this benchmarking using BERT base model. So I'm just gonna write here BERT base uncached. So in this benchmarking we are going to train our model over these 4 model: BERT base, DistilBERT, MobileBERT and TinyBERT, and then we will be seeing that how fast the training is for each of these models and what will be the accuracy difference if we use these models. And thereafter, based on those findings, then finally you can decide that which model you need to use into the production. Okay, so I write here def train model, and in this I need to pass the model name. So that model name will be passed from here because we will be iterating over this model dictionary. So just for a completeness, let me write that for loop. So here it will be for model name in model dict, and then we will be calling this method, which is the train model, and in this we will be passing the model name. Now this model name will be returning here the accuracy, so that I can say that as the temp something like this. And this I'll be storing into model performance variable. So I write here model performance is equal to a dictionary, and in this I can say that model performance and then the model name is equal to the temp. All right, or you can say that as a result, maybe that would be a better name to say that. Now this result I need to return from this train model, which will be accepting this model name. Okay, so these are the things here. Let's go ahead and write this overall training inside this train model. So we have here a compute matrix. This compute matrix we will be using into the trainer. But before that, few things we have to write here, like we have to get the model checkpoint. So these will be the model name. So that's the model checkpoint. So for that I need to verify, I need to rewrite this model CKPT is equal to model dict, and from there based on this model name I'll be getting which particular model I'm going to use, that is the model checkpoint. Thereafter I need to again get the tokenizer, a fresh tokenizer. So I write here the tokenizer is equal to auto tokenizer from pre-trained, and in that I write here model CKPT. Thereafter I need to get the model. So model is equal to auto model for sequence classification, then from pre-trained, and in that I write here model CKPT. Because this model checkpoint is only variable things here, other things like the number of labels and other things will be same. So I write here number of labels is equal to the 2, and rest of other things you can write as it is, like we have seen previously. Let me just get that. Yeah, so this whole thing actually you can write. So I'm just gonna copy that whole thing from there, and then I'm just going to paste that here. Okay, so this is the model, and thereafter once you have the model, now I need to do this tokenize method internally, because this tokenizer had changed. Now if this tokenizer had changed, then I have to write that tokenizer method internally. So it's a kind of the local function there. So where is that tokenizer method? Yeah, this one. So this becomes now a local function. So I'm just gonna call this from here, and then I'm just gonna use that internally. So another way you can also maintain a tokenizer the dictionary, where based on selected model name this tokenizer can be changed, but I'm just going to use here another local function inside a function. So this tokenizer will be used based on this model name, and then on the title it is going to tokenize the data, and now we have to do this tokenization on the dataset. So I say here encoded dataset is equal to dataset.map, and in that I call you can see that local tokenizer, maybe a better name, that would be a better name, local tokenizer. I say here, sorry, what is this, local tokenizer, and then I say here batched is equal to true, and then I say here batch size is equal to none. That's how this overall tokenization is going to happen. And then I'm just gonna copy this trainer function from here. This whole thing I can just simply copy from there, and then I can paste it here. Okay, so in this trainer, what is different here? So the model we are already getting from here. Compute metric is different. So this time we are going to use this compute metric, and thereafter other things are same, only this tokenizer is different. So here I'm just going to use this tokenizer which I have initialized there. So there is a trainer. Now once that is done, then you can just call here trainer dot train. So this will be now trained, and then finally you call the prediction, where you say here trainer dot predict, and there I'm gonna do the prediction on encoded data's test set. So I write here test. Once that is done, then you can return here preds.metrics. So this is the same thing what we had seen here, preds output.metrics. So it will be returning those metrics from there. So I write here preds.metrics. Once that part is done, then this will return here in result, and that will be stored into the model performance. Now we need to just run this. So this is going to iterate over this whole model, all of the models, or I can just simply interrupt this and then I can print that. Probably that would be better way to say that. Training model, and here I say model name, and just before start that I print here 2 double new lines. It's kind of that. Okay, so it says that it is training BERT based model. Now it is going to take some time. I guess that it will take around 10 to 15 minutes for all the model training. So we have a 4 model here. The maximum time will be taken by the BERT model, thereafter DistilBERT, then MobileBERT, and then the TinyBERT will be super fast. So we have to wait like 10 to 15 minutes for the benchmarking. Once we get the benchmarking, then we will again start this lesson. Okay, I'll see you then. Alright, so model training is done here. We have trained BERT model, DistilBERT, MobileBERT, and TinyBERT model. Like we have seen here previously, it took around 20 minutes probably to train everything. Yeah, it took around 24 minutes. And result is stored into model performance. So I'm just gonna print here model performance just to see that how much, how much performance we are getting for each of these models. So in BERT base, we are getting test accuracy of 95%. In DistilBERT, we are getting almost same accuracy, 95% and 95%. In MobileBERT, we are getting a slightly less accuracy, but I can say that almost same accuracy for each of these. And then in the TinyBERT, I also see here that we are getting almost same accuracy. So for this particular problem statement, we see here that we are getting almost same kind of accuracy for all these the models. So with this, what do you learn? With this, you get to learn that in production, it's not necessarily that you will always get a good accuracy with BERT base, but you won't get with the TinyBERT. That's not the true. So sometimes these models, which are a smaller model, might fit better in your use case. So always try to do a performance benchmarking, something like this, and then see which model is doing better for your data set. Okay, accordingly, then you can decide that which model you need to choose. If there is a large accuracy gap, then you can accordingly select that which model you want to choose. Otherwise, out of these 4, I see here that the TinyBERT model accuracy is same as all other 3 models. I would definitely choose this TinyBERT model. Another important point you need to notice here that the test runtime. So test runtime for BERT base is okay. Seems like this is not correct. This doesn't seems like correct. For this, it says that here 6 seconds. Here it's 6 seconds. Okay, seems like this is definitely not the correct things. I'm not sure how this has came here. This shouldn't be here. So the reason is here that this you see there the test runtime is not the true here. So this is definitely not the correct, because previously I have seen, let me just show you, maybe that would be better way to show you this. Just a second, let me show you. Okay, so in this previously I have seen that the model accuracy was almost same, but the time taken by all these models were different. Okay, because I can show you, let me show you my sample file here. So in this, what happened here, I printed this model performance. So let me just zoom zoom in this one so that you can see it properly. So I printed here the model performance. What I see here for BERT base model, test runtime was 4 seconds. For DistilBERT, test runtime was 2 seconds, and for MobileBERT, test runtime was 2 seconds. But for TinyBERT, test runtime was 0.5 seconds. And if we see here the difference between BERT base and TinyBERT, we see around 8 times of the model performance, which is almost equal like how the research paper has claimed. Okay, so the somehow seems like while this training we could not store this test runtime properly. That is why these test runtime for BERT base, for DistilBERT and for TinyBERT seems like is coming almost same. So what to do to get that performance which I had just shown you? So what to do to get this performance? So what you can do, you can actually do one extra step since it takes a lot of time. So I'm just a little bit reluctant to train it again, but yeah, you can do that. So what you can do here, you can import time here and then you can put time here. Okay, so you can put time here. Okay, so I see here start is equal to time dot time. So this gives you start time for your model when model training has started, and then you can say that end is equal to time dot time, and thereafter you can store this here. So now I'm just gonna put this into another dictionary, a dictionary of dictionary. In that I say that it is going to be here a model name. In that I store this result, and thereafter time taken, that's the another dictionary. In that I say that here end minus start time. Okay, so this one will be a better performance measurement technique. Okay, perfect. So with this model performance you have, and then the model name. So with this it will train it, and in the model name the result will be stored and total time taken will be also stored separately. Now it will be independent how the model is internally getting the trained, because we have noted down here the time before model has started, and we have also noted down the time here after the model training is done for a particular model, and then we have stored here. Let me just verify that if something is missing here and same kind of model is being used, maybe that could be the reason. I see here the model dict is there. In the model dict we have BERT base, DistilBERT model, MobileBERT and TinyBERT. This seems correct. So these models are getting changed, that is fine. Thereafter we have here the model name, so that is getting printed every time which model we are going to use. From model dict, model checkpoint, tokenizer is getting used, and from this model checkpoint a new model is getting loaded every time. Let me just see here in the config, maybe we might have done something wrong. Probably this old config which have previous models, maybe because of that this problem is coming. Oh yeah, because of that problem is coming, because this model config have this model checkpoint, the previous model checkpoint. So that is why that problem was coming. That is why I thought that when I did it offline I was getting a better the result, but here I'm not getting. Okay, I'm sorry for that one. So just to solve that problem, what you can do here, you can recreate this config here. So here you have a model checkpoint, and then this config is there, and then this model is here. Okay, now this problem should be solved here. Anyway, so we have also added here start and end just in case if there is any problem, and I'm again going to run it, and then we will connect like after 30 minutes, and then we will see that we should be able to get a better model performance. All right, I'll see you then. All right, so training is finished here. Let's go ahead and check it out here. So once all training is done, then you can just print this model performance. Now you see the BERT base took around 12 seconds, whereas DistilBERT took around 6 seconds. So it is half of the time of this one. And thereafter MobileBERT took around 23 seconds. That seems odd. And then the TinyBERT took around 3 seconds. So if you compare this TinyBERT with the BERT base, you will see that it is a lot faster than the other models. But here we have also noted down these time. So in this time it says that this one is actual time. So I'm just gonna copy these things at a single place so that you can understand this, that one, and then I copy this one, and thereafter I copy this one, and thereafter I copy here this one. Okay, so this time 679, this was for BERT, and this was for DistilBERT, and here it was for MobileBERT, and this one is used for the TinyBERT. So seems like in this case MobileBERT took a little bit more time as compared to the BERT base. So this says that at least for our the problem statement, seems like MobileBERT took more time as compared to the DistilBERT and TinyBERT, even the BERT base. Okay, but if you compare this TinyBERT, so it took around 100 seconds, whereas this one took around 680 seconds. So you can simply divide this. Okay, so you can say that it is 6 times, basically you can say that 6 to 7 times faster as compared to the BERT base. Okay, so this is all about in this lesson, and if you want to save your model, you can simply save your trainer dot save. Okay, so here you can see the save model, and here I say it as fake news, and I just save this. Okay, so once I save this, I see here a fake news, and here is the config. In the config, I see the TinyBERT model is saved here. The reason is TinyBERT model is saved because when I ran this for loop, in that for loop last model which ran, that was the TinyBERT model. That is why it is saving the TinyBERT model. If you want to save all of these models, then you can simply use that train.save model inside the function itself, here itself, so that the trainer will get saved. I mean to say that the model will be saved for each of the for each model, you can say. Okay, you can also see this config, a detail about the model type, and then you can see the special tokens, tokenizer configuration. You can also see the tokenizer and full list of the vocabulary, and here is vocabulary is also separately available, so you can go inside each of these files and then you can see these. Okay, once you have saved your file, thereafter you can simply you can simply load your model. Let me just delete all these. Okay, so you can just simply copy that from here to here, and now you can use the pipeline to do the prediction. So the pipeline again is pretty much straightforward like we did in our last lesson. Here in the last lesson we have a pipeline. You can simply just use this pipeline. Okay, so this pipeline can be directly used there for the prediction. So I'm just going to use those pipeline. So from transformers import pipeline, and then I say here classifier is equal to the text classification, and then I need to put here the model name, and the model name is fake news. So this has loaded this classifier. Now inside this classifier you can put some text data, and then this will get classified, and it says that this is fake news. Okay, so if you put here a real news, that will get classified as the real news, otherwise that will get classified as the fake news. Okay, so this is all about in this lesson. Thanks a lot for watching this. I'll see you in next one.